Hi, everybody. It's Professor Mitchell. We're continuing Chapter 2 from OpenStack's Intro to Business Statistics for MATH1610. Last time we talked about stem plots. So the next type of graph we want to talk about are line graphs. Here you see an example of a line graph. This is referring to a specific example in the textbook. They surveyed a bunch of parents and asked them how many times do they have to remind their teenage children, say, to do their chores. So the way that I read this is two lucky parents said that they don't have to remind their children at all. They do things the first time they're asked. 5 parents said they have to remind their children 1 time. And then 8 parents said they have to remind their children twice. And then if you continue going on like that, there are 4 poor parents who say they have to remind their teenagers to do things 5 times before they get done. So along the bottom, you have your data, which should be labeled. You know, the person reading your graph should know what they're looking at. And then the y-axis represents the frequency. So let's look at our own example. In a survey, 40 people were asked how many times per year they had their car in the shop for repairs. So the results are summarized in this frequency distribution. You see that 7 people said they never had their car in the shop. 10 people said they had it in 1 time. 14 people said they had it in twice. And 9 people said they had it in 3 times. So on the next slide, I'm going to show you what this line graph would look like. I made it using Excel, and it looks something like this. So along the bottom, you see I have my axis labeled. Number of car repairs is either 0, 1, 2, or 3. Here are the 7 people who said that they never had to have their car in the shop, going up from the 1. There were 10 people that said they had to have it in once. 14 people said they had to have it in twice, and 9 people said they had to have it in 3 times. So that's a line graph. Next, we have bar graphs. So I know you've all seen examples of bar graphs. Bar graphs are a really popular way of presenting data. You see them in newspapers and on TV. You see them everywhere. So along the bottom, in this example, you have ages. And I can't remember what the context of this example was. But, I think it was social media use, if I remember correctly. So 45% of the people on a certain social media platform are 13 to 25 years old. About 36%, it looks like, are 26 to 44. And then a little less than 20%, maybe 19%, are 45 to 64. Bar graphs are really good for summarizing categorical data, especially. In this case, it's summarizing quantitative data. Okay, so our example of a bar graph is going to be very similar to the one you just saw. A population in Park City is made up of children, working age adults, and retirees. This table shows the 3 age groups, the number of people in the town from each age group, and the proportion of people in each age group. And they want us to construct a bar graph showing the proportions. So for this example, we don't have to pay any attention to the numbers of people. We're not going to use those. We're just going to put these as our categories along the bottom of the bar graph. And then we're going to use these as our frequencies. Okay, they can also be proportions. Frequency would be a raw number like this. So if you look at what I came up with, again, using Excel, we've got the categories written across the bottom, and then up going along the y-axis, we have the proportion. So here's the 19%, Here's the, what was it, 43% and the 37%, something like that. One thing that people will sometimes do to make a bar graph even easier to read is to actually write that percentage either on the bar or maybe on the top of the bar. And then the person looking at it doesn't even really have to look over here. All right, that brings us to histograms. Histograms are very similar to bar graphs. The difference is that histograms are always used only for quantitative data. And when you see a histogram, you'll notice that the bars are all stacked against each other. And the reason for that is because your data is quantitative, you want to make it very clear when you do and don't have missing data. So a gap between bars in a histogram would indicate that there's some range of data that had zero frequency. Okay, and I believe in the example I'm going to show you, you'll see that. So again, you have a horizontal axis and a vertical axis. The horizontal axis is labeled with what the data represents. Vertical axis is either the frequency or relative frequency, or it could be a proportion. So all of that's the same as if it was a bar graph. Okay, so, and then the relative frequency, if you choose to use that instead of raw frequency, that is the frequency for an observed value divided by the total number of data values in the sample. The time when you definitely want to use relative frequency is if you're comparing two different groups. We had an earlier example where we were comparing De Anza and Foothill colleges for number of full-time and part-time students. That would be a good example of when you would want to use relative frequency because the two colleges were different sizes. So the raw numbers would not necessarily tell you the whole story if you were comparing them. Okay, so, excuse me, this slide goes into a lot of detail about how to construct the histogram, and you'll see all this in the example. First, you want to decide how many bars you're going to have in your histogram. 5 to 15 is a good range. Okay, so just decide how many you want to have. Let's say you decide you want 8. What you would do next is you would look at the range of your data, okay, the lowest value to the highest value. Take that range and divide it by the number of bars that you want, and that will tell you sort of how big an interval each bar represents. And again, you'll see this in the example. Now, your book has a convention that I really like, actually, about how to label the endpoints. So what they say to do is to look over all your data and see what is the largest number of decimal places that any of your data has, okay? And then you're going to start your histogram at a value that has one more decimal place than your data point that has the greatest number of decimal places. So, for example, right here, if the value with the most decimal places is 6.1, in other words, only one decimal place, and if that happens to be the smallest value, then you could start your histogram at 6.05, okay? So in other words, just go one additional decimal place and then go halfway down, you know, not all the way down to 6.0, but halfway, which would put you at 6.05. If the value with the most decimal places is 2.23, so 2 decimal places, and your smallest value is 1.5, the fact that you have a value with 2 decimal places means you want your starting point to have 3 decimal places. So go from the 1.5 down to 1.495, right? So always end it in a 5 is basically how that works. And then if all your data is integers, which is a pretty common thing, then you can have your starting point start with 0.5, like a 1.5 or a 6.5, depending on what the smallest value is. And the reason for doing this, when you add the additional decimal place, it means that no data value will fall on a boundary, which is a really, really nice thing to have. I can tell you that in my other statistics class, which uses a different book, they don't do this. They just have them use as their endpoints, you know, numbers that can be in the data. And then there's sometimes a lot of confusion about, you know, should I include that value there, or should I include it here, or where should I include it? So this is a kind of nice way to do it. All right, so here's the example for histogram. The following data are the shoe sizes of 50 male students. The sizes are continuous data. I have to make a confession to you. I don't know that I really agree with that or not. As far as I know, shoe sizes are either always whole numbers or half sizes. We didn't really get into this in class a lot, but the fact that these data can't just be any old decimal, I would actually call these discrete, okay? But that's okay. So we're going to construct the histogram and calculate, and in order to do that, we're going to have to calculate the width of each bar, all right? And they're telling me to use 6 bars. So in a statistics class, they will often tell you how many bars to use. One thing that I like about that as the instructor is that if they tell you how many bars to use and you follow, you know, the rest of the directions, then everybody should come up with the same histogram, which makes my job a little easier. So here's all your data with all your shoe sizes. So the shoe sizes range from 9 to 14. Notice that the greatest number of decimal places is 1 decimal place, which means that we're going to start at the 9 and we're going to go down by 2 decimal places down to 8.95. So our starting point will be 8.95. And you don't have to really worry too much. Well, I'm sorry, I take that back. And then since the largest size was 14, you'll go up to 14.05. And since we've chosen to use 6 bars, our class width will be the difference between 14.05 and 8.95. Divide that by 6. That comes out to 0.85. And your book suggests rounding that up, say, to the next whole number. Okay, it doesn't have to be a whole number, but that just makes it a little bit easier. So we're starting at 8.95 and we're going up by 1s. Each of our classes will have width 1. So the first class will go from 8.95 to 9.95, which for shoe sizes really means 9s and 9.5s, right? So I counted those up on the previous slide, and I believe there were 4 of those. From 9.95 to 10.95, there were 14. 10.95 to 11.95, there were 20, et cetera, et cetera. Interestingly, nobody was a size 13 or 13 and a half. So that class has frequency 0. And there was 1 person who was a size 14. Okay, so you draw the histogram and it ends up looking something like this. Now I have one suggestion. Again, I did this in Excel and I could not quite figure out, there was one thing I couldn't quite figure out to do. When you're drawing these, especially by hand, what I would like you to do is actually put the class endpoints on the sides of the bars. In other words, put the 8.95 here, 9.95 here, 10.95 would go right there, 11.95 would go there, et cetera, et cetera. Okay. But notice there are no gaps between the bars. That was something that I actually researched inside Excel to figure out how to do. That was very important to me because I wanted it to be crystal clear that when you do come to this gap here, it meant that there were no values in that range. Okay. Remember, there was nobody who was a size 13 or a 13 and a half. And that's how you do a histogram. All right, that brings us to the next section, 2.2, measures of the location of the data. All right, so in this section, we're talking about quartiles and percentiles. Well, let's talk about percentiles first. I think it makes more sense to talk about quartiles once you know what a percentile is. Okay, so roughly speaking, I remember the first time I encountered percentiles, it was when they make you take those standardized tests when you're in elementary school. And back in my day, you would take the test, and then a few months later, they would mail your parents a report of how you did on the test. So, and they were always reported in percentiles. So if you score in the 80th percentile on a reading test, it means that you scored better, as well or better than 80% of the people who took the test, and 20% of the people who took the test did as well or better than you. Okay, so that would be 80th percentile. Percentiles divide data into hundredths. So you could have first percentile, second percentile, third, fourth, fifth. You can also divide your data into quarters, and that gives you quartiles. So the quartiles that you hear about the most often are the first quartile, which is the 25th percentile. That is a score, roughly speaking, that separates the bottom 25% from the top 75%. And then the third quartile is the other way around. That separates the bottom 75% from the top 25%. And then there is such a thing as a second quartile. The second quartile is the same thing as the median. And we'll talk about that a little bit more later. Okay. Percentiles are generally used in very large data sets, and they're useful for comparing values. All right, so let's say I'm teaching two different statistics classes. You know, I mean, one class might be at 7 o'clock in the morning, and the other one might be at 11 o'clock in the morning, and sort of attracted a different groups of students. So, you know, an 80% on an exam in one class might be very different from an 80% in the other class, relatively speaking. All right, it might be more special in one class than in the other. And so that's the reason that percentiles are often used to compare values. Another really common one is the SAT or the ACT. Those tests that you take to get into college. All right, so their example here, suppose that Duke University accepts SAT scores at or above the 75th percentile. So in order to get into Duke University, you have to have an SAT score in the top 25% of people who take the SAT, and apparently that translates into a score of at least 1220. All right, so obviously we have to talk about how to calculate percentiles. First, let's talk about the median. So again, the median is also known as the 50th percentile or the second quartile. Basically what the median is, it's the middle number. However, that does create an issue when you have an even amount of numbers. So let's see, this example here, they have this set of data, 1, 11.5, 6, 7.2, et cetera, et cetera, et cetera. So to figure out what the middle number is, first you have to put those values in order. And then you need to know how many there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 14 of these. So when you have an even amount of numbers, you can try to find the middle, but what you find is that there isn't a middle 1, there are actually a middle 2. So in the case where there are an even amount of numbers, what you have to do to find the median is find the middle two and then average them together. So that's what you see done here. The middle two numbers would be the 7th and the 8th numbers. To find the median, add those two together and divide by 2. So you're finding the mean of the middle two, and that comes out to 7. When there are an odd amount of numbers, that makes it easier because then there will be one in the middle, and that middle one would be your median. Okay, so now we can talk about how to find percentiles. There are several formulas for calculating the kth percentile, and I can tell you that's true because the book that I use in my other class uses a different one. All right, so what they have you do, first let's define a little bit of notation. K is the percentile that you're trying to find. All right, so like if you were trying to find the 80th, K would be 80. And then I is called an index. So basically the index refers to what position is that value in. So if I came out to 14, that would mean we're talking about the 14th number from the bottom. And then N is the total number of data points, the total amount of numbers. Okay, so the steps to finding the kth percentile. First, you put your data in order from smallest to largest. Then you calculate your index. And the way that your book calculates the index is a little different from how my other book does it. You do K over 100 and multiply that by N plus 1. Right? And that number will either come out to an integer or not. Sorry, I see this auto-corrected to a capital I. So if that number comes out to an integer, for example, 14, then the percentile that you're looking for is just the 14th number on the list. However, if that number doesn't come out to an integer, let's say it comes out to 12.2, then you would take the 12th and the 13th numbers, that's what they mean by round it up and round it down, and take the average of those two. So take the average of the 12th and the 13th. All right, so let's do an example. We have 29 ages for Academy Award winning Best Actors, and they were nice enough to already put them in order. So they want me to find the 20th percentile and the 55th percentile. Okay, so I've done that on the next slide. All right, so for the 20th percentile, the first thing I'm going to do, if it hasn't been done already, is put the data in order. Then I'm going to calculate my index. So let me walk you through this calculation. K over 100 times N plus 1. K is 20. We're trying to find the 20th percentile. There were 19 values. So we're doing 20 over 100 times 30, and that comes out to exactly 6. And since that is an integer, that means the 20th percentile is just the 6th number on the list, which if you look back at the last slide was 27. So what that means is that an actor who wins an Academy Award at age 27 has 20% of the other winners have been 27 or younger, but 80% of them have been 27 or older. So 27 is relatively young to win this award. Okay. At this point, you might want to pause the video and see if you can find the 55th percentile. I'm going to be quiet for a minute and give you a chance to do that. So just pause the video and see if you can find the 55th percentile, and I will wait for you right here. Okay, so hopefully you've paused the video and you've tried that. So basically works the same way. It's already in order. Find your index. So k over 100 times n plus 1 would be 55 over 100 times 29 plus 1. And this time that comes out to 16.5. Obviously, that's not an integer. So we're going to round that down to 16, round it up to 17, and take the average of the 16th and 17th numbers, which are 52 and 55. So the 55th percentile would be 53.5. So 55% of actors who have won this award were younger than 53.5, and the other 45% were older. All right. In some problems, the data is given as a frequency table. So here's an example of that. 40 bus drivers were asked how many hours they spend each day running their routes, rounded to the nearest hour. Find the 65th percentile. So it's roughly the same steps. There are actually a couple different ways to do this, but I wanted to show you the one that's always going to work. All right. So the first step, put the data in order. That's basically already done when you have a frequency table. So now I'm going to calculate my index. And I'm finding the 65th percentile. So 65 over 100 times 40 bus drivers plus 1 comes out to 26.65. And remember, when that index does not come out to be an integer, you round it down and round it up. So it's going to be the average of the 26th and 27th. Now the trick is, how do you pick out the 26th and 27th smallest numbers from a frequency distribution? Well, you just have to know how to read it. So looking back at that table, the first 12 observations were 2s. Remember, there were 12 2s. And the next 14 of them were 3s. So that's a total of 26 observations that are 2s or 3s. So if you imagine this data just in the form of a list, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, and then a bunch of 3s, the 26th number on the list would be the last 3, wouldn't it? And then the 27th number on the list would be the first 4. So the 26th number is a 3, the 27th number is a 4, so the 65th percentile would be the average of those two, 3.5. 65% of bus drivers answered 2 or 3, and the other 35% answered 4 or more. All right, and then I have one more thing to show you relating to percentiles, and that is, suppose they give you a list of data. For example, we're going to work with the list of ages of actors again. And if there was a 70 on the list, you know, somebody won the award at age 70, finding the percentile for that. Okay, so here's how you do that. Again, put your data in order from smallest to largest. And then you have to find a value called X and a value called Y. And here's what those mean. So X is the number of values that are less than the data value that you're looking for, the number that are less, and Y is the number that are equal. Okay. So let's say, again, you're trying to find the percentile for somebody age 70. Count how many actors won the award age less than 70. That would be X, and then count the number of actors who won it at age 70, and that would be Y. And once you have those two numbers, you calculate the value X plus 0.5Y. So take how many numbers are less, and then half the numbers that are equal. Add those together, divide by the total amount of numbers, and what that's going to give you is a proportion. The times 100 just changes it into a percentage. Okay. And then round that to the nearest integer the way that you were always taught how to round, right? If the first digit after the decimal point is 0 through 4, you round it down. If it's 5 through 9, you round it up. So let's do an example. So here are the 29 ages for Academy Award winning Best Actors. They're already in order. They want me to find the percentile for a 58-year-old actor and the percentile for a 25-year-old actor. So let's do that. Before I go on to the next slide, I think it might be useful to show you where I'm getting some of these things. So remember, the two ingredients that go into this formula are how many numbers are less and how many numbers are equal. You call those X and Y. So when I go to find X for the 58, I count how many numbers are less than 58, and that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 numbers are less than 58. Only one number is equal to 58. Okay. So X is going to be 18. Y is going to be 1. So you put those into the formula. 18 plus half of 1, and then divide by 29. Converted to a percentage comes out to 63.79. So when I round that to the nearest whole number, it comes out to 64. So a 58-year-old actor who wins this award is at the 64th percentile. So roughly speaking, 64% of people want it younger, and the other 36% want it older. So the next example is the percentile for 25. Whoops, I was going to, well, you know what? Pause the video and try 25. Okay. All right, now we'll look at that. Okay. So if you go back to the previous slide, there were only 3 actors that won the award younger than 25, and then there was one value listed that was equal to 25. You put those numbers in the formula. 3 plus half of 1, and then divide by 29. Converted to a percentage comes out to 12.07. The nearest whole number would give you the 12th percentile. So a 25-year-old actor who wins this award is at the 12th percentile. Only 12% of people who have ever won this award were 25 or younger.